radios. This session will be focused on QSD and its role in processing signal using digital signal processing, offering a deeper understanding of how SDR technology is revolutioning amateur radio communication. Guiding us with this technical, exciting journey, I would like to call on stage Somnath, call sign Victor Uniform 3 Foxtrot Bravo Tango. Over to you.
Okay, till the time he is organizing, starting the presentation, my name is Somnath De, call sign VU3FBT, and I'm an agriculture engineer, BTech by profession, and MBA finance. So I've been doing finance work for a very long time, for donkey years, like 20 years now, and I'm a ham for the last 4 years. So this is my journey into electronics. Software-defined radios. So basically, it's a part software and part radio. So I'll try to keep it short, very, very short. I know the last session, everybody wants to go home. Okay, next slide. Okay, these are the topics I'll cover. Introduction, history, evolution, and pretty much everything about software-defined radios. I'll try to not bring in a lot of technicalities into it for the ease of understanding. So it will be a bird's eye view, nothing very technical. Okay, next slide. Okay, what is an SDR? It's a radio system where traditionally hardware components are replaced by software. So let's say, I'll give you an example, your cell phone. It's a SDR. So most of the things which the radio is doing through software, the Android system, and with a very limited hardware. Okay, and yeah, programmability, flexibility, multifunctionality. Yes, dependency on hardware. So you know, hardwares they have a tendency to fail. So you know, they get old, the components degrade, and they die. But in SDR, you can preserve the software, run it in another hardware later on. So you just need to clone the software to another hardware, and you can keep on running the radio for a very long time. Okay, next slide. Okay, in 1960, the digital signal processing was invented. What we call the inception of the DSP, and in 1984 E-Systems developed the SDR prototype. 1991 Joseph Mitola called his team developed a software radio. 2000 we saw its commercial implementation into the cell phone industry, the telecommunication industry. Okay, and now today is SDR is the integral part of modern wireless and communication system. So every wireless, every communication system is an SDR, software dependent radio. Next slide, please. Okay, these are the key components of a SDR. So we have the radio frequency front end. I'll try not to use as little as abbreviations. I'll try to not to use. We have radio frequency front end. We have antennas, filters, and amplifiers. So the antenna will get the signal. The filters will filter out the unwanted signals, and the amplifier will boost up whatever signal it is receiving. Okay, then we have analog to digital converters, digital to analog converters. So signals are analog, they will convert it into a digital type, and then they will be fed into a computing system. And reverse. So Your computing system will generate a digital signal. They will go to an analog amplifier, and then you will hear out the analog audio through your ears. That is analog. I'll not go deep into implementation, protocol and control logic. And what in between, what the third point means, we are using something called DSP, digital signal processing. It's a full semester topic in electrical engineering. It's a big concept, so I'll try to cover, touch upon it. Next slide. Okay, working principles. RF signals received through antenna. Here the antenna is receiving the radio frequency signals. The ADC, the analog to digital converter, is converting the analog signal to digital. Then it is feeding into the software. Digital signal is processed in the software, and then the software is processing the signal and giving out the desired output through a tag, which is called a digital to analog converter, and then what you can hear, or you can demodulate, or you can do whatever you want with the signal. Next slide. Okay. Yeah, we pretty much know what are the benefits of SDR. Next slide. Dada, next slide. Okay, let me come to some drawbacks of SDR. No system is foolproof, no system is great. There are drawbacks also. Yeah, high power consumption. Analog systems are not high power consumption systems. They used to draw very low power. But because of SDR technology, these systems are very highly dependent on high processor speed and they have a demand for a high GPU. Artificial intelligence, which is being rolled out right now, also has a very high dependence on hardware. There is latency. Of course, there is latency. Latency means lag. So SDR might have some latency issues. Why? Because the software may take time to process the signal. We have our security risk and software vulnerabilities. We are obviously SDRs are prone to cyber attacks. Why? Because these systems are generally online, and they use software. They are generally MCUs, IoT based, or they are running on computers. So yeah, these systems, if not air gap, can be really problematic. The fourth one is the most complex. You need very deep knowledge of DSP and programming. So to write a software-defined radio, you need to know assembly level C. That's a very advanced level. And you need to know DSP, digital signal processing. So you need to know what is a fast Fourier transform. You need to understand Fourier transformation, Hilbert transformation, and other ways of numerically interpreting signals. Converting signals to mathematics. Okay, next slide. Application, we have SDRs are in cellular networks, 4G, 5G. I think 6G also, it is the same thing. We have in military, we have secure adaptive communication in battlefield environments. All radios nowadays in military is SDR. Public safety, we have emergency response and disaster recovery. People have control bases and control centers where they are using SDR to monitor all the airwaves for the disaster frequencies. Satellites, they are all SDRs because we have flexibility in that. And of course, we also use SDR experimental uses by us, the amateur radio world. Okay, next slide. Okay, some software tools. You can search the internet, GNU Radio, one of the greatest open source tool which you can obviously use in a Linux environment. SDR hash, that is also a very good tool. MATLAB, then hardware tools are USRP. These are generally academics in universities, like people who teach electrical engineering, where they use this universal software radio peripheral, where this is needed to teach as software-defined radios. HackRF is one SDR, Grade RF, and there are many more examples. Okay, next slide. Challenges, yes. ADC and DSE limitations are there. Very fast ADC, very fast DSEs, analog to digital converters, digital to analog converters. They are difficult to get. Yeah, but as day passes, we are getting better chips, but at very high cost. I built a radio a year back. The ADC chip was somewhere around 16,000 rupees. It's only the ADC chip, and it gets hot as anything. So yeah, noise is another problem, because SDRs are very sensitive. They are very prone to noise and distortions. So while writing the code and designing the software, these things has to be taken care of. Regulatory constant, compliance and spectrum allocation, this I will not cover. Next slide please. Okay, this I think pretty much is clear now. Analog radio, they are all analog, all parts. Software is some parts, and then the rest of the thing are all softwares. So hardware dependency is low, flexibility high, cost over time. Yeah, these things don't get bad. They get old, but they don't get bad. Yeah, next slide please. Yeah, I'm rushing through all the slides because I think the time is very less. Next slide please. Okay, future trends. Yeah, AI, artificial intelligence with SDR is a deadly combination. So it can do a lot of things like adaptive modulation and spectrum sensing. AI can detect half of WPC's work might get automated by AI. They can automatically sense spectrum, and then they can record, and they can keep it for later monitoring. So these things are already there. They have already come. I'm telling future, but it is already there. 6G is and beyond technologies. They have all SDRs built to it. Yeah, IoT is obviously a part of SDR, and SDRs are now being embedded into IoT systems, like there is RAK Wireless, who have developed chips which has SDR capabilities, Bluetooth and LoRa. Then you have Nordic. Nordic has chips which are also very capable on NFC, Bluetooth, and there are many other companies who are developing this on the chip radio, which can do a lot of stuff with very low power. Means you can practically use a AAA, AA battery and run it for a month. Okay, next slide. Okay, so I'll come to the context of this radio, what you see on the table, and this is a very basic software-defined radio, and I've used something called a Tylo quadrature detector, QSD. That's what it's called, quadrature sampling detector, and it was conceptualized by Dan Tylo. Okay, just take it very lightly, not with salt, but take it very lightly. Don't try to get deep into it. Whoever wants to get too deep into it can contact me directly. But this is on a lighter note. We have RF, which is coming in, radio frequency, and Then we have a box over there which is called 4 into F0, F0, and we are getting 4 baseband out. The radio frequency is being converted into 4 signals, which has a 90-degree phase shift on the second one, 180-degree phase shift on the third one, and 270 phase shift on the fourth one. Don't get into details how it is being done. If you want, I will cover. If you don't want, I will not. So that's a black box, and we are immediately getting the signal into the black box, and we are getting 4 signals out. That is what being done in this radio. So these 4 type of signals which has a phase shift, sine wave. So sine waves, they have phases. So one can be 90 degree apart, 180, or any amount of degrees apart. But here we are making a 90 degree, 180 degree, and 270 degree and 0 degree signal. Why we are doing this? We'll go to next slide. These 4 signals we are calling it baseband. Next slide, Dada. Okay, this is your typical RF signal which is coming in. The first one is the 0, second was the 90, and then 180, then 270. So we are splitting that signal into 4 parts, and we are taking out those 4 signals. The next part. Okay. Now we are feeding that 4 signals into putting that 4 signals into an op-amp. Now it's very difficult to make you understand here what is an op-amp is. It is called an operational amplifier. It's an electronic component. It does a lot of stuff, but mainly it does amplification. It does detection. So it does a lot of stuff, but here we are using it for some amplification and combination. So what you see over there are 2 gates of the op-amp, and we are combining the opposite signals. So we are combining the 0 and the 180 degree part of the signal, and the 90 and the 270 degree part of the signal. This is called a differential op-amp. ये IC जैसा देखने में होता है, looks like an IC with 8 legs, 4 legs on left side, 4 legs on right side. That is what we are doing here, and then we are recombining it in this staggered manner, opposite manner, and we are calling one signal I and one as Q. All SDR radios, whatever you get across from a $10 SDR to a $10,000 SDR or a $10 million SDR will have I and Q. Okay, everybody is trying to make I and Q. So whenever you go into SDR, DSP, you need I and Q. So first idea is to make I and Q. So that is how I am doing it, the I and Q over in this radio. Okay, next slide. Okay, so the RF is coming in, getting converted into 0, 90, 180, 270, then going into the operational amplifier and getting I and Q. So first 2 diagrams were in separate slides. Now I will combine the entire circuit to understand how the signal is being processed. The next slide. Okay, this is somewhat the circuit what I have used here. We have something called a local oscillator, which generally sends a signal to the demux, or we call it a multiplexer, demultiplexer, which is actually the black box which I called in the first slide. That's actually called the multiplexer, demultiplexer. So this all stuff is happening inside the radio, and we are getting I and Q out. Next. Okay, this was the first prototype which I built 2 years ago. Looks good? Not good. Yeah, it worked. Yeah, it worked. It received signal, it sent out signal, but it was very noisy. It was very noisy. Why? Because I was using all through-hole components, and I think because of that or something else, it was generating a lot of noise. But it worked. Okay, the next slide. Okay, this is the second prototype which I made. This worked really good. Now, what I have in this radio is called a double balance quadrature sampling detector. This was a single quadrature sampling detector. So the input signal was not impedance matched to the output of the radio feed. So for that I was not getting good sensitivity on 10 meters. Plus the audio amplifier which I was using was not up to the mark, and it was having distortions. So this is the second prototype. Then I changed, go to the third prototype. Tada! This is the third prototype what I made, and this was successful. But what happened, I had to do a lot of rework on the board. Though this I have successfully operated. In fact, I went to Balasore, put up a Yagi in Devashish's house, and we made excellent contacts with very low power. A few of the videos are there in my YouTube channel. You can have a look. Okay, Dada, next slide. Okay, the final version is on the table. It's all aluminium. It has a computer connection. You can do CAT control. You can take the I and Q. I explained over there. You can take the I and Q out with a simple aux jack, auxiliary jack. Put it into your computer, run HP SDR software in your computer, and you can see the spectrum display which this radio is receiving. So this radio lets you take the I and Q out and process it in your computer. And plus it's tactical. You can carry it along. Unfortunately, I cannot switch it on. You cannot. Here it is a HF radio. It is a 9-band SDR. Covers 80 meters to 10 meters. It gives 5 watts output. Unfortunately, we will be only making 50s, and we will gift out this to a few hams here. Okay, to the next slide. Okay, this is the future development. I'm working on something which you can see. In fact, this will have a waterfall display. You will have a waterfall display. You will be able to see the signal, where the signal is, actually who is there on the band. It will put a lot of show, but it will do the same work which this is doing, but it will have a lot of show and stuff and all. So you will be able to see the waterfall, and you will be able to select, and a lot of flexibility. You can see this. You have your AGC. This also has an AGC attenuator. This also has an attenuator. Preamp. This also has a preamp. And yeah, means a bigger screen, a lot nicer to look. This I'm working on right now. Okay, Dada, next slide. Okay, this is something which I didn't develop. This was developed by a team led by VU3FBT, a Russian developer. He developed this radio. It's called the Wolf SDR. So it looks very beautiful with all colorful displays. It's a 7-inch screen and extremely beautiful to look and talk and walk and This is the true epitome of and true technology of SDR. It covers 10 kilohertz way around to 1 gigahertz. You can receive and you can transmit, and pretty much all band, all mode, everything. Classic example of an SDR. I have this. I built it with my own hand, but this is something somebody else has developed. But it's an open source project, so I did it. Looks very beautiful. Okay. Thank you.